Evan, thank you very much. And everyone, welcome to Scale by the Bay. It's a privilege to be invited back to speak here. I love this conference. I've made a lot of friends and learned a lot of things over the years. And I'm here to talk to you about location-based data engineering for good with PySpark. That's kind of a long title. So we'll dissect that and what it means. So just a quick word from my employer, Urban Logic. What we are is, imagine that you could do data science with a lot of cool data from maps, location data, all kinds of things, and you could present cool visuals and help your community improve how it plans itself. That's basically what we do. We are a software platform that presents, analyzes, and does machine learning data science on data to provide insights for cities, counties, states, etc. And we use Rust, Python, machine learning, and stuff on all kinds of interesting use cases, some of which we will go into today. So location-based data, what is it? Well, everyone uses their smartphones. And when you use your phone, you use apps that oftentimes report on where you are for various reasons. This could include maps, but other apps will use it, like apps that serve ads, which are almost all of them does this. So for better or worse, you get there's this data that comes from all kinds of different mobile providers. It comes from Google, Apple, etc. And there's a large variety of this data with different coverages and densities. And it can be used for a lot of purposes, but what we like to use it for is to process this and condense it into notions about where people are coming and going, and that can help with all kinds of analysis to improve your communities. So let me give a couple of examples. Example one has to do with what we call amenity and accessibility planning. So imagine that we're talking about, for example, parks in a city, right? So who visits, or where do people who visit these parks come from, and where do they go afterwards? How can planning for city parks, their locations, what recreational facilities they have, for example, like if they should have a dog park or not, how can they be planned better? What kinds of people are most served or least served by the existing parks? And if a city was to zone another park, where could it be placed to serve underserved populations? Right. So what we can do here is that we can turn this location-based data into notion of origins and destinations for people that visit parks, like where did they come from, where did they go? And this can help people plan. This can help cities plan where the parks are and plan what kind of amenities they should have, like disability, this kind of thing. Another example has to do with transit planning. So here what I'm showing are origins and destinations for people traveling through transit, in this case, subway links here in Vancouver. And the different colors basically represent origins versus destinations for people coming through transit. So by looking at this data, after we aggregate it from the raw data, we can visualize travel patterns and figure out for folks that are traveling on this transit route, how effective is it? If we were to extend, if the transit route was extended, where could it go? And so there's a lot of usefulness to planning transportation. A third example would be what are called play streets. They are apparently very popular in certain parts of the world, but the idea is that we want to close off portions of city streets to provide play spaces. And this is great, especially for families. You can have a lot of just a lot of space in a lot of neighborhoods, there's a lack of play spaces. So this is something that really helps. And by combining location-based data, traffic data, demographic data, we can help inform good potential places to implement this kind of policy. So I hope these examples give you a flavor of a broad use of location-based data to help improve our communities and cities. So now let's switch to data engineering. So we want to build pipelines for processing this data. And what are some of our goals that we would have for producing these pipelines? Well, we want them to be scalable, to be able to handle bigger loads of data. We want this to be reproducible, that we can run with the existing set of data again and produce consistent results, right? We want these pipelines to be flexible and easy to maintain, so that we can go in and someone else can come in and understand it and tweak it for whatever purpose. We would like to be productive, right? So these are all goals that we'd like to meet. Currently at our company, we use a framework, a Python framework called Kedro. So what is Kedro? So Kedro is a framework for producing structured data pipelines. The way it works is that you set up a directed graph of nodes, and the nodes transform data. You can think of inputs and outputs like data frames, so they can transform data frames to something else, and then you can take the output and transform it. And Kedro produces a really nice visualization here, where you can see for each node, which has the f function, right? This is basically a node. It's essentially just a function that takes input, transforms it to some output. Underneath, it could be doing something very, very complex. And you have data inputs and outputs, and you have parameters. And based on those, that would power your pipeline.
Hey, Evan, we have a question here.
Absolutely.
How does Kedro compare with Airflow?
I'll just give a really quick answer, because I will talk about Airflow later. Yeah, Airflow is an orchestration package that can orchestrate a lot of data processing. I would say there are very different focuses. Kedro actually works with Airflow, but Kedro is not focused on orchestrating and scheduling and running the pipelines. It is more how to organize pipelines into a DAG. So it's a bit of a simpler abstraction. But yeah, we'll talk more about this a little bit later. And I will talk about Spark. Spark, everyone uses Spark by now. I use Spark since it was in the 0-point-something days, when very few people had heard of it. But now everyone uses it, and now Spark supports Python very, very well. I guess it's a big deal because Python is so everyone uses it in the data world. So the way I compare these two is that so Kedro, being just an organizing framework for pipelines, supports Spark, but typically when people start out using things like Kedro, the base version is people are using pandas with it, which is single node, and all your data basically has to fit in memory. But you can then plug in PySpark into it, and now you end up with a pipeline that is scalable, and is distributed. It is still written in Python and still written at a very high level with high-level transforms, but your data does not have to fit in memory, and you can work with all of the huge number of deploy options or productionizing options that you get with Spark. So with that out of the way, let's get into what I call origin destination inference. This is a method of extracting trips or origin destination pairs out of location data. So we'll look at how we can do this using PySpark. So the overall processing steps are, first, we want to normalize and sessionize our data so that we get it by device. Then we want to coalesce these events. So basically what happens is, you can imagine one event is your phone like sending in a ping to say, I'm at this location at this time, basically, right? So that's one event. Now, so in order to create patterns out of it, the first step is that we want to coalesce these events that are in what we determine to be the same location. We want to coalesce that to a single duration event. Then we use inference to determine and turn these events into trips or origin destination pairs. And finally, we can sort them and get them together. So the initial steps, we read some data out of our favorite cloud data store, and Spark can just read this data directly out of the cloud, and select some data, which is this is actually a really cool. I know this will be like super simple to all of you that work with big data. I was just going to point out that this is actually a really big deal to folks who don't have a big data background, because packages like pandas, for example, actually cannot do this. They just work with single files, on your local, machine. But you have to add other plugins to be able to do this. So it is really cool that Spark can actually read whole directories worth of stuff, and then you can usually sort your data state by device ID easily in one line, right? But it's pretty cool. We take this for granted, but there's a lot going on under the hood when we do this, right? And so the initial output we get might be something like this, where you see there's a whole bunch of this data that is sorted by device ID. And now we can analyze, the patterns of events that we get. So what we want to work with are windowing functions for coalescing data. The windowing functions, the way this works is that we have a sliding window that goes over the data. And you can see that I highlighted a current row. So what you imagine is that a window will start from, like typically it starts from the current row and goes backwards, so it kind of goes like this. Excuse me for a minute. I need to mute something really, really quick. Okay, sorry about that. So basically the window is, you have this window over rows of data. So imagine the window goes, kind of, it's a little bit hard to highlight, goes kind of like this. So typically there's two directions you can go. So windows, you can look backwards, which is called lag. So you can see the index goes -1, -2, -3. So you can look backwards, or you can look forwards, which is called a lead function, which is kind of neat. You can actually look ahead. And we're going to use that. So the first step is that we want to figure out, well, how far is my current event from my last point? So you notice that we start by doing a window.partition by and order by. This will divide your data into events for each device and ordered by time, which is really convenient, which is the order we want to go through things. Then the way that we compute the distance from the previous point is that we take the latitude and we subtract from the previous latitude, which is using this lag function. And one means that we're going one row back. And we do this over the window. And then we compute the hypotenuse distance by doing the delta of the latitude and longitude. So pretty simple. And we see the output here. Where we see the null is basically, well, this is the beginning of this device ID, so there's no previous row. And so you see for the ones that are the same, we get the 0 as we would expect. Now, once we have the distance from the previous, what we do is that we want to group events. We want to group a bunch of events that are at quote unquote the same location. So to do this, we add additional columns for first row and last row. And what first row means is that we want first row to be true, the first row in a group where where it stays the same. And the way we can tell that is by looking at this distance that we just computed. If the distance from the previous one is above a certain threshold, then we would count that as not staying in the same location. So therefore, it is now the first row of a new group. The last row, so this is really neat. We figure out the last row of a group by seeing if the next row has first row equals true. So this is an example of a look ahead. And this is really neat that you can do this. It sets up a kind of, this is all very high level, but this creates like, very interesting state. After we have the first and last row markers, now we can try to compute statistics. So let's start with a really simple one. We can count the number of events that happened between the first and last row of a group, like how many events there was when someone stayed at one place. And the way we do this is by starting another row. So you see there's a lot of these another column. There's a lot of these temporary columns. And what we do is that we track the row number when first row is true. And otherwise we output a null. And then we have this neat function called last, where we can look up the value from the first row. And so we would just take the current row number and we subtract that, and now we get the count. So, and so we would repeat this across everything else that we want to aggregate. And we can end up with this coalesced output, where for each row, basically you're looking at, you're looking at, hey, this row has 41 events. Someone was there 41 times, and they were there, like for 18 hours, at this location. So this allows you to then do a lot more inferencing around trips. There's a couple of different methods. The easiest method would be to use statistical methods, statistical thresholds. So you can say that an origin or destination is when the device has stayed at, X location for Y minutes, or the number of counts is above a certain amount. So you can use kind of fixed thresholds as a really simple start to infer some. It works okay. You can do smarter things. Like you can say, on average, a lot of people just go to and from work, right? So we can make an assumption that the location with the longest dwell time is likely to be the home location, and the second longest on a weekday might be an office, and you can confirm that based on their travel patterns and so on. You can combine several of these and make things a lot smarter using things like k-means clustering. So you can use all these methods to try to infer trip information. And then we need to check it work. So all these inference algorithms have some bias, such as using homework locations is biased towards a standard work lifestyle, right? With kind of fixed home, fixed work inference. And so there's certain, populations you are probably biasing against if you use a method like that. And they all need a lot of experimentation with a lot of parameters. And then you validate it and you come up with an idea of where the trips are. So, and then after that, then analysts at the cities and other places can use this work and hopefully improve our transit and other things like that. Another area you can go, which is really neat, is that you can use graphs for analysis. So here, what I've done is to aggregate my location-based data into a graph with counts. So I've put strategic locations such as transit stops and neighborhoods as nodes as a graph. So you can see here I have a node called neighborhood 1, stop A, stop B, and so on. And at stop A, I can see where people are coming from, that they're coming from maybe another stop or some neighborhood and another neighborhood. And I can see the mode of transit that they're coming in from. And I can see where they're going. I can see that, people from stop A like to walk downtown, but some of them might take a bus to another stop and so on. So when I aggregate this data in a graph, I can do this analysis and traverse some nodes and figure out travel patterns beyond just origins to destinations. It can figure out really, really interesting things, see where bottlenecks are. So this is a pretty powerful technique that is underexplored. All right, so we've talked about processing and doing inference on location-based data, which is really neat, and I think you'll see a lot of examples of this like today and in the future. But I'd like to now switch to the last half to talk about just data engineering and producing reliable pipelines. So this is a really huge space because there are, I would say that as a data engineer, you can spend pretty much all of your time just keeping up with all of the projects that are happening in this space. And there's a really huge amount. But the common concerns, everyone needs scheduling, orchestration, failure handling, retries, observability tools. And there's such a large range, right? Like you can start with a super simple setup with something like Kedro or some other basic pipeline tool with just base Kubernetes stuff. You do get some resilience that way. More likely, folks would use something like Apache Airflow. So really, like someone had asked about Airflow before. I look at Airflow as like so Airflow provides you with a directed graph also, but it also does orchestration, also does scheduling, and so it's a much higher level thing than Kedro. Kedro is more like a the directed graph piece in Airflow. I think Kedro actually does it slightly better than Airflow, but Airflow is much more complete, right? So Airflow is also, there's a lot of cloud environments that support Airflow, and there's even websites that have hosted Airflow. So there's astronomer.io. I don't know if folks have used them. It'd be actually, if whatever folks have used, it'd be great to get their feedback on how some of these. There's obviously MLflow, and there's other similar frameworks. And MLflow itself is really popular and hosted in various places. You have cloud-based solutions like Google Dataflow and Databricks and other things that are more specific. And finally, you have even higher level, you have some specific, like you have a lot of cloud or paid solutions that are really, they are more like complete, like ETL kind of pipelines. And there's Taboola and other things like that. I will switch to talking about quality engineering. This is a really big deal nowadays because data bugs are not like service bugs, because it's not enough to fix and redeploy it. And going back to fix old data is really expensive. I find that so there's a lot of good data quality frameworks. I just listed two. That there's a really standard one in Python world called Great Expectations. It produces these pretty reports. And I found one that is specifically for PySpark, where you can write a SQL, which is kind of neat because it allows more people to be able to write these tests or assertions on data. I think whatever data quality framework you use to catch stuff, I think the important thing is like how you incorporate it into your methodology. There's a lot of, basically this is the ops part of data engineering. Things need to be set up. you need to have a way for people to regularly get these reports. You need to alert on them, right? And I think data versioning will also be really key. So using things like DVC, DLT, et cetera. Being able to compare different versions of your data so that if you do fix it, you can see what was fixed, right? And finally, observability is really important, right, for data pipelines. And I guess my comment on this space is that this is a space with a lot of movement. I'm interested in hearing your takes. As someone that worked on observability, but more traditional app observability, my observation is that there's a lot of tools that aren't always a great fit for, like if you just use standard metrics and monitoring frameworks. Oftentimes it's like circle and into a square, a square into a pig. Well, yeah, you know what I mean, right? So they don't quite fit that well. Like, for example, metrics infrastructure is typically designed for long-running processes and not designed for transient jobs. They don't make it easy for you to compare different pipeline runs and stages. Logging tools are oftentimes not easy to use, or not helpful they are helpful, but when you have more complex pipelines and complex stacks and distributed data systems, then they become really difficult to trace what's going on. I think that you'll see like the use of tracing tools and a lot more specialized data pipeline tools. I think you're seeing this already, but I think you'll see more and more very specialized data pipeline or data observability, ML model observability kind of tools coming out. And this is a space that is very exciting. And this would be a great topic to chat about too. And that is what I have today. Thank you very much for your time. Feel free to reach out to me on Twitter, GitHub. I have a webpage there, or Instagram if you like photos. Yeah, thank you very much. I think, Devin, I don't know if we have time for a question, or we should